So we're back with some of the questions from the My Math Lab homework on section 11.2, and these will be a mixture of problems that have you practice the derivative rules using exponential and logarithmic functions, a little bit about using properties of logarithms, and finally some more application problems. So the basic derivative rules are, again, fairly simple to add to our list of formulas that we have. Just like always, we sort of go left to right. We're going to leave these plus and minus signs alone. We're not going to worry with them. And we're also going to leave these constants that are out in front alone. So as I go across finding the derivative here, I would leave my 6 alone, and then I would find the derivative of the e to the x function. Well, that's just e to the x. That's why we like e to the x in calculus. Plus, right, I'm not changing the plus, 5 times x, that's 5 times the derivative of x, which is 5 times 1. The derivative of 5x is 5. And then minus, I'm pulling this minus sign down. And then the derivative rule for natural log of x is just 1 over x. So that's our correct derivative for that expression. So you see that it's not really hard to add that to our basic rules. We are revisiting these tangent lines because I don't want you to forget what the derivative is measuring. These questions about do they pass through something or don't pass through something, those are just sort of hokey questions to ask, but ultimately what you really want to do here is find the equation of the tangent line. That's really the right first thing to do for all of these problems. So I want the tangent line at x equals 3. So to find the tangent line equation, I first need the slope of the tangent line. So I'm trying to find the slope of this red line. Well, it's actually at 3, so here. So the slope of that red line is measured by f prime of 3. Well, to find f prime of 3, I first need f prime of x. So the formula for the derivative here is, well, the 4 is a multiplier out front, so I just bring that down, and the derivative of log x is 1 over x. So when the function is 4 times log x, the derivative is 4 times 1 over x. So therefore, f prime of 3 is just 4 times 1/3, which is 4 over 3. So that means the equation of that tangent line, I'll have y minus blank equals 4/3 x minus blank, and the blanks have to be filled in with a point on the line that you know. Well, the only point on this line that I know is the one right there that I'm told that this line goes through. So that has x coordinate 3, so I'll put 3 in the blank that goes with the x. And the number here is going to be the natural log of 3, whatever that is, because that's the y coordinate on this curve when x equals 3. So in my calculator, I find the log of 3 is let's call it 1.1. So I would have 1.1 here for my equation. So this is the correct equation of the line. Now, should you rewrite that in slope-intercept form? Well, that always just depends on what you're going to do with it. In this case, it asks, does it pass through the origin? Well, the origin means the point 0, 0. So I can tell that from this equation. I don't need to rewrite it to tell that. Passing through 0, 0 means that if I put in 0, 0 for x and y, then that should make this equation true. So I can check, is this equation true? Is 0 minus 1.1 the same thing as 4/3 times minus 3? And it's not too hard to figure out that that's not true. So no, this is not a true statement. This shouldn't be 1.1. Oh, it's 4.4. Because it's 4 times log 3. Sorry about that. I misread the problem. 4 times log 3. So this should be 4.4 over here. But it's still no. There's no way that these two things are equal to each other. And so I would check the box here for no. But that's how I can answer these questions. First, find the equation of the tangent line, and then plug in whatever point it's asking about. And if this gives you a true equation, then the answer is yes. Otherwise, the answer is no. There are a couple questions like this where they ask you to use some rewrite properties first. And this is worthwhile just because it reminds you of the rewrite properties. Our properties of logarithms tell us that the log of 13x is the same as the log of 13 plus the log of x. The log of a product is the sum of the logs. So the 13x is still there. So as I find the derivative of this, the derivative of 13x would be 13. Then, and now I'm saying this is the same thing here, the thing in the box. The derivative of the log of 13 is just 0 because the log of 13 is just a number. I don't know what number it is, but you can put it in your calculator, log of 13, and see that it's just a number. So the derivative of a number sitting up by itself like that is 0. And then plus, and the derivative of log x is 1 over x. So the correct derivative here is 13 plus 1 over x. Finally, we have an application problem. It's a problem that asks about depreciation, and there are several other questions, but I'll just answer the first piece here. The rate of depreciation, that is the change in value. So that's asking about s prime of 1. Why 1? Because that gives us the first year. So depreciation is a rate of change of value. So to get that, I need to know the derivative formula first. So the derivative of the formula in terms of t. To find the derivative of this formula, I would bring that 700,000 out front because that's just a constant. And then I would find the derivative of the piece that's left, this piece. The derivative of any number to a power is just that exact same number to a power, but because this base is not e, it's a different number, I have to multiply by the log of the base. So I get this extra number out here, and you shouldn't fool around with those. You should just use a calculator and get that to several decimal places. So if I do that, let's see, the log of 0.8 is negative 0.22, yada, yada, yada. So if I simplify this, I'll have 700,000 times that number. So I'll have negative 156,200 times 0.8 to the t. That is my derivative formula. So it's simple enough to put 1 in for t or whatever else it asks you for t. And you can see that that's a negative number, so that's why this is called depreciation, because the value is going down.